Thanks for joining today's colloquium. We are very happy to have Professor Martin White from Adelaide University to give the presentation today. So Martin got his PhD from Cambridge, UK, and had postdoc appointments at Cambridge, split with CERN, then at Melbourne Uni, and finally he settled in Adelaide. So he's interested in a whole range of topics in astrophysics and particle physics, from dark matter to beyond the standard model theories, gamma ray astronomy, over quantum information and machine learning. And today he will give us his view of the challenges that we have to tackle in particle physics. So the floor is yours. After the talk, there will be tea and cookies just behind you, and Chaba will convene the question session at the end.
Okay, thanks very much. So thank you for the invitation to come here. It's taken a while to get here because I was on sabbatical and so on, and it's great that it worked out. And you know, tea and cookies itself is a nice piece of evidence of why it's amazing to visit Monash, and it's just a great place in general. So the title of this is "What's Next for Particle Physics?" It's actually borrowed from a book. I think this has stopped working. Okay, here we go. It's borrowed from a book that I wrote for the UK Institute of Physics a few years ago now. And the idea of this series, it's quite a nice series, is that it surveys the research frontier in kind of 30-page booklets for a third-year undergrad that's going into research in some area of physics. So the idea is they get to kind of shop around by reading these books. They can't be too long, or you should never read them all, and they get an idea of what's going on. So the idea of this was to get into particle physics and why I think it's still a very active and exciting field, but at third-year undergrad level. So it will be quite a gentle colloquium, I hope, but that hopefully means it's quite accessible to those who don't just stare at Lagrangian densities all day. So I started here. Once upon a time, there was this famous quote, "There's nothing new to be discovered in physics now. All that remains is more and more precise measurement." And that is attributed to Lord Kelvin. He looks like a lord. He's dressed like a lord sometime in the late 1890s. And of course, like most convenient fictions, he never said it, right? Anyone who knows anything about Kelvin would know that he was sufficiently close to the dawn of the quantum revolution that he could never have been fooled into thinking there was nothing, right? It's actually, we think, we being the internet, Albert Michelson, who said this sometime in 1894. He doesn't look like a lord, but close, right? So there's nothing new to be discovered, and we know this, and of course we know what happened next, right? This is very, very far from more and more precise measurement. The one that always blows my mind is galaxies, because we're so used to living in a large universe, we forget that it's only about 100 years that we've had this knowledge, right? But the basic point is, of course, there was lots of stuff around the corner, and you know, pessimism at that time was somewhat unwarranted. So if you go to 2025, and owing to the vagaries of facial hair, the person looks a bit like Lord Kelvin, right? And they say, there's nothing new to be discovered in particle physics now. The LHC saw the Higgs boson in 2012 and nothing else, right? Indeed, Melbourne has sort of led the charge in this kind of sartorial elegance as well, I think. I'm going to explain, I'm going to spend an hour telling you why I really, really think this is untrue. I'm going to try and cross-reference some of the most exciting work that's come from the LHC, which is from the LHCb experiment that in Australia happens here, which I'm not involved with, but I'll try and mention that as we go through. My background's on the Atlas detector, and I'll explain what that is, and I'll explain the Higgs boson and what's new, right? But at third year kind of undergraduate level. Okay, so what do we know about particle physics? This is the sort of basic stuff, you know, what do we actually know about the world? This is the kind of slide which is well below the level of the average colloquium, but it's a nice intro. You know, we know about atoms, we zoom into the atom, there's a nucleus, there's electrons, there's things in the nucleus. That jump from there to there cost me, I don't know, £30,000. You had to go to university to learn that. They could have told you it only takes 5 seconds, right? You did, of course, learn to drink large amounts of whiskey, but that in the end was also unhelpful, I think. That's what we know. But of course, we have other particles as well. So the fundamental particles in nature are these. And of course, most of your protons and neutrons are actually those, and atoms are fleshed out by this thing. and we have these neutrinos. You know, seeing neutrino astronomy start as a field has been one of the amazing stories of the 21st century. The idea that we can actually now disentangle the leptonic and hadronic components of cosmic ray studies, for example, by using neutrino astronomy is an amazing thing. We have heavier versions of each of these particles. Why do I say that's a heavier version of that? It has the same quantum numbers. It's just got a larger mass. And the top quark, you know, is the heaviest fundamental particle we've ever seen. And I think most of us who work in BSM physics think that the top quark and the Higgs are kind of the windows. Those are the things to understand. Yeah, I say that because the top quark is the thing that interacts with the Higgs field most strongly. We have the idea that we have forces that mediate interactions between particles, right? So we have the gluons being the strong force. We have the W and Z bosons for the weak force. We have the photon for the electromagnetic force. And then, as we'll see, we need something called the Higgs boson. And I'll try and explain in some sort of physics detail why that's necessary without resorting to analogy, but again, at third year undergrad level, okay? So that's the real standard model. That's what it actually looks like. And the main point to make here is it's a very precise mathematical description written in a language called quantum field theory. So the idea is that we have matter and forces represented by fields filling all of space. I think it's Anthony Z's book that has a mattress of springs, you know, as a sort of intro. And if you bang the springs, you get excitations. They can wobble around, they can interact with other excitations. And for those who do non-relativistic quantum mechanics, where you're used to sort of wave functions, what's nice about a QFT is it's a way to organize the degrees of freedom so that you can have processes where number density changes. You can start with 2 particles, you can end with 4 particles, right? You can have a shower of particles, which is what Peter does, right? You can have all sorts of things happening, right? And that's why a QFT is a useful organizing principle in how you do the physics, right? So the particles are the excitations of the field, and the vacuum isn't empty for reasons you're not allowed to know because of Zoom. But in a quantum theory, yeah, in a classical field theory, I can have a classical field theory. GR is a classical field theory, and it doesn't fluctuate around its vacuum state. The difference with a quantum field theory is it does, right? I get fluctuations around the vacuum state, and we'll come back to that idea, okay? Okay, now the standard model allows us to make precise calculations. It allows you to make precise calculations. Everything I'm showing you here, within an hour of sitting in my office, you would have learned how to do that in a computer on Mathematica. It's quite straightforward, right? So, yeah, this is a Feynman diagram. We have some quarks coming in, sort of Q bar. We have Z boson making some muons. And if you've never done this before, the important thing to realize is that's not really just a picture. It's not like a diagram when you're doing a first year exam and you sort of draw a diagram of a pendulum or something. It's a precise calculational recipe, right? I can attach a piece of maths to each of these pieces of the diagram, and then I've literally got the equation that I have to calculate to work out the rate of this thing occurring or something, right? So it's a precise calculational recipe, and it's automatable. You know, nowadays you can just type your equation into a computer and it will generate the diagram and calculate it for you. And a very central idea we'll come back to is the idea of perturbation theory. If I'm in a regime where the force is weak enough, then I also get this as a higher order contribution. It's suppressed relative to the first diagram. It involves more vertices with a coupling in, which is a small number. So, you know, like when you're summing a series and you can truncate it at a certain order, you can truncate this series when you've got to the precision of your experiments because you don't need to go any further, right? But the idea is I have these loop contributions that give me extra things that can happen in my Feynman diagram, and they contribute to the measured things that I have to calculate for colliders and so on. So think about if I had new particles beyond the standard model, they can now enter those loops and they can shift the answer to something beyond the answer I naively expect. So that's an idea that we're going to come back to. Okay. So the standard model is not just a set of quantum field theories. It's a set of special things called gauge field theories. And I want to understand the gauge bit because I want you to understand why the Higgs is necessary, right? So forces, it turns out, arise from the invariance of the Lagrangian density under various abstract transformations, and those are called gauge transformations. And we can actually motivate this, if we're talking to a third-year undergrad, through something they've seen, which is classical electromagnetism. So I was in my second year when I first saw Maxwell's equations. Every year in a physics degree is taking you further from the ability to calculate something easily with a theory of electromagnetism. Brian Weber in Cambridge used to joke that the point of a physics degree was eventually you could write Maxwell's equations like that. And he's not too far wrong, actually. But of course, we can write these things. And then this absolutely baffled me as a second year because we weren't told why. I can write the B field as the curl of an A field, and I can write the E field as minus the gradient of a scalar field. And so, have you seen this before? Yes, lots of nods, right? So you'll know I can take the A field, and it's not unique. If I add the gradient of a scalar potential, the properties of a curl mean that the B field are the same. And the B field is the physics, right? So I get the same physics when I do that. And if I change V in the same way, well, not the same way, but in a similar way, I get the same thing for E. And those of you who've gone a bit further will know I can actually write this as a 4-vector equation where you can even see the relative minus sign that would creep in Minkowski space with a sort of 4 gradient, right? And so I can write this as a generally covariant tensor equation in 4 vectors, which is why you do this in the first place, because it's easier, right? And that's then true in all frames. So that thing is for historical reasons called a gauge freedom. It's a gauge transformation. I can pick a gauge to work in, but I have to get the same physics if I change the gauge. The equations are gauge invariant. The physics doesn't change if I change the gauge. And that is a sacred principle in the Standard Model. It's a sacred principle. I mean, the posh version of electromagnetism is called QED. Gauge invariance remains at the heart of the theory. It has to, because Maxwell's equations have to be in that theory somewhere, right? And the theories of the strong and weak force are generalizations of QED. So what you find is, if I take some equations and I say, I want them to be invariant under the transformation that gives me electromagnetism, that thing we've just seen, I have to add terms to the equations which make me get the same answer out of a gauge transformation, and the term I add is the photon field. So the idea is that the force results from the gauge properties of the theory. And then you can apply the same thing to the strong and the weak force, and you get valid gauge theories, and you can measure what the gauge group has to be in that case. So again, I cannot hammer this enough. The gauge principle is absolutely sacred in the formulation of the Standard Model. So the problem is, that's fine if I have massless particles, because I can, the photon, for example, is fine because it's massless. But there's no way to easily add mass terms which protect gauge invariance. If I add mass terms, they're not gauge invariant, right? So I can write a mass term, and then I can do a gauge transformation, and I can't cancel off the extra bits. So how do we get mass terms? We have to add another field called the Higgs field. And this is an extra scalar field. It's the only scalar field, fundamental scalar field in the Standard Model. It has a non-zero vacuum expectation value. So the way I do that, I can add a field, and I just give it a potential, which is not, you see, this is the problem here is I actually have to draw. But let's add a potential, and it's just, its lowest value is not at the 0 point, right? So if I then take the average energy of the vacuum, it's going to be non-zero, right? That's the idea. And it turns out that if you add that and you expand around the new vacuum, because I want to now look at my quantum fluctuations around the vacuum state, which is now not the state before I added the Higgs, then I get mass terms which are fine, and I get mass terms for the fermions and the force particles. And the key point is that the Lagrangian density, the equation I showed you before, the big long Standard Model equation, is still invariant under the gauge transformations. I haven't broken gauge invariance. I've had what's called spontaneous symmetry breaking, where at some point in the universe it cools down and picks a vacuum state, and I expand around that because of this funky potential, and I get my mass terms, right? So it is absolutely baffling to me that the thing we see at the LHC seems to be that, right? Because the potential is sort of just added. I mean, I know it came from condensed matter musing and things, and it's a simple way to do it, right? Arguably the simplest way to do it, but it didn't have to be that. And it's a tremendous mystery why that is the case. It's in some sense a phenomenological solution, and it's something I'll come back to, okay? So how do we discover the Higgs? You know how the LHC works. It's a circular collider. You put protons that way and you put them that way and you smack them together at very high speeds. It's 100 meters underground. That shields it from cosmic rays and so on. I always say it's actually because it's 100 meters under Geneva is more exciting than being on the surface. Exactly, not true. There's plenty going on in Geneva. There's plenty going on in Geneva, much as there is in Canberra. But no, it is actually an exciting city, and of course, one of the reasons it's exciting is precisely because you have so many. You know, you have like World Health Organization, you have UN offices there. It's just a crazy sort of melting pot of different influences. So there is fun to be had. Okay. Okay, so what does the LHC do? That is a sort of real cartoon of protons coming together and lots of crazy stuff happens. Here you can see things called outgoing partons and final state radiation, and that's a ludicrous simplification of Peter's entire career getting that bit right. It is. I mean, it's much more complicated than that would suggest. It's a very complicated business. What I like to think, if I'm talking to sort of first-year students, the way I like to think about what the LHC really is, it's a full momentum bucket filler, right? I put full momentum in, and we don't always use protons. We use heavy ions some of the time. And we fill a bucket with full momentum. And of course, what quantum mechanics and relativistic quantum mechanics allow me to do is I can pour that full momentum into different things. So I can pour it into the rest mass of new particles. So I can make new particles, and their rest mass has to be filled from my full momentum bucket. And then those particles can move, right? So some of that full momentum has to go into the motion of particles. But that's what it is. It's a full momentum converter. And then I have general purpose detectors in the case of Atlas or CMS that were designed to discover the Higgs and anything that might be beyond the standard model that can be seen sort of produced directly. And what these do is they measure, and I have to remember this because of Zoom, but you basically get the full momentum of particles, you get the identity of particles. So is it an electron? Is it a muon? Is it a jet? Jets result from quarks and gluons being made, and then the non-perturbative nature of QCD makes funky things happen, and the sort of strange QCD potential makes funky things happen. And we also get, you know, some idea if we've seen something called a B jet or the sort of heavy electrons and so on. But that is it, right? So the whole job of LHC physics is I'm only given that, and I have to guess what particles were produced. Right? There's nothing in the detector that says you've made a W boson or you've made a Higgs boson or you've made anything, right? I only see the decay products that particles produce, and I have to infer what was going on in the collision. And we'll see later, we have all sorts of things that happen randomly at the LHC. You can't pick what's going to happen. And the backgrounds to new physics processes are absolutely colossal, right? You know, to first order, every single event here is a dijet event and everything else is a tiny correction, right? It's something like that, or at least a multi-jet event. Now, something I haven't shown here because I'm coming from the Atlas CMS background is LHCb. That has a very different design. It's a forward detector, and it exists to do very precise measurements of things called B mesons and their properties. And arguably, the most exciting anomalies and hints for new physics are coming from LHCb, not Atlas and CMS. And I'll try and sort of motivate that as I go through, okay? Let's understand the Higgs discovery in detail. I'm sure you're familiar with this four-vector analysis because you're beyond third-year undergrads. Let's say I have a particle in its rest frame and it decays to n particles, and I stopped at 3 because I couldn't be bothered to draw a sort of infinite n. If I apply full momentum conservation, that has a full momentum p mu. They all have some pi mu, and if I sum them up, that has to equal what I started with. Yeah, that's my full bucket filler, full momentum bucket filler. If I square both sides, that gives me the invariant mass of the particle. And the key word there is invariant. So I don't care what frame I'm in now. I can measure those full momentum in the lab frame at the LHC, and I get the invariant mass. Right? And on the right-hand side, it's just the invariant mass of the sum of these. Right? So that gives me a way to measure the masses of particles that are decaying to things that I actually see. So if this is a Higgs boson, and then there's only 2 of them, and that's a photon and that's a photon, I should look at all the events with 2 photons in, and I should add up their full momenta and take the invariant mass. And what this theory without quantum mechanics tells me is that I should see, if I plotted a histogram of those events, something like a delta function up to binning at the mass of the Higgs boson. In fact, it's not quite a delta function. Quantum mechanics gives you a finite width for particles. You'll have seen that before. By far, the biggest effect is exactly the same thing that screws you up if you're doing astrophysics and you're trying to find line features with an instrument. It's the finite resolution of the instrument, right? So I don't measure 4 vectors entirely accurately. And so when I actually do it, I get this, right? And most of that bump is the detector resolution, right? But, so this is quite simple. You take all the events with 2 photons in. Yeah, I'd say quite simple. You spend 6 billion and you get 30 countries to agree to spend 6 billion and you build a big tunnel, you know, all that stuff. But you take all the events with 2 photons in. And yeah, you do some cleaning because you want to make sure they're real good photons. They're not kind of fake signatures or something. Now, the standard model without a Higgs can make a pair of photons in various ways. You know, here's some quarks coming in, photons coming out. There's a box diagram. You know, it's less probable I'm going to make high energy photons there than low energy photons, so I get a smoothly falling background that looks like this. I always say to students, if you don't know what a background looks like, it could be astrophysics. Well, astrophysics, it's a power law, usually. If it's particle physics, it starts up there and it ends down there and it does something like that in the middle. I mean, that's the law of backgrounds, right? Of course, the Higgs, because of our very, very simple 4-vector analysis, we literally get a bump at the Higgs mass, right? I mean, that's what we saw in 2012. Well, not this. I think, is this the... No, this is not a discovery plot, is it? This is a later plot with more data, which is more dramatic. You know, the challenge, one of the frontiers of statistics is what happens when that bump is kind of that. And you've organized a big press conference and you want to convince the world you should win the Nobel Prize and you've got to get the stats right, right? So when people talk about big data problems being hard, they're not hard. I mean, Claude Code and ChatGPT just does it now. Small data problems are hard, right? Small data, the regime where a frequentist and a Bayesian are literally at war because they can't agree on the answer, right? So there's a whole army of people worldwide, people like Karl Kramer, you know, really studied that problem for a decade to get that right. Okay, now the position of the bump gives us the mass of the Higgs. The height of the bump is also important because the height, yeah, if Higgs bosons are produced more often, the bump goes up. If they decay to photons more often, the bump goes up. So the height of the bump is kind of sensitive to the product of the production rate and the decay rate to photons. Is that clear? Right, good. So this is our current Higgs knowledge. This is one of the update slides that I grabbed since writing the original book. And this is all the different ways you can make a Higgs that we've observed so far. You can make it with a Z boson. You can make it in what's called gluon-gluon fusion or vector boson fusion. You can make a Higgs and a W boson. This is relatively new. You can make a pair of top quarks with a Higgs and so on. This is all the different decay modes: B quarks, gauge bosons, tau leptons, Zs, photons, muons. And seeing this is just awe-inspiring, frankly. That's a very, very small signal to pull out. And this is the product of the production rate and the branching ratio normalized to the standard model expectation, right? So if the standard model's correct, all of these data points should line up on the red line, which is just showing you what the standard model predicts. Standard model, ooh, massive uncertainties, right? So the key here for the future, one of the futures of the Higgs program is, you know, if I shrink error bars, can I do it? If I do an error bar and it shrinks, and you know what happens usually because life's shit, it shrinks and it goes there as it shrinks, right? And what we want, you know, one day we will see this happen where something shrinks and it shrinks there, right? There's evidence that's happening in cosmology, right? But you know, LHCb, I think that's what's happening. Actually, I really, really do. Here, I think what's happening is it's probably going to go around there, but we have to go to much higher precision. Okay. Definitely standard model-like, and so on. So what we see at the moment is something that looks very, very, very much like a standard model Higgs boson, right? And it doesn't preclude other things, but it sets limits on what those other things could be, right? If we go beyond the Higgs, I think they call this is a Led Zeppelin plot from CMS. They called it the Stairway to Discovery plot, which I quite like. So there's a version of this which is played in every guitar shop in Australia. And what's happening here, this is you won't be able to see anything even from the front, I think, but the theory prediction is this kind of thing here. You can see these little grey boxes. These are a whole bunch of different particle production processes at the LHC. And this is the production cross-section. So there we go. There's the sort of inclusive jet cross-section. And, you know, there's, what's this? W and Z production, they are an order of magnitude smaller than what's going on over here, right? So it's a pretty, you know, it's pretty hard to see things as soon as you go out here, right? They're very, very small production cross-sections. But the message of this is that the production rates for particles at the energies of the LHC are very, very well described by the Standard Model still, right? Okay, good. Right. So having told you, oh, you know, this is rubbish, this idea that there's nothing new to do now except more and more precise measurement, I've just shown you some very, very precise measurements, and that's it. So why am I confident that there's more to do? We know that the Standard Model can't be the final answer. It famously doesn't include gravity. I don't actually expect it will include gravity within my lifetime, actually. I'm not saying I'm going to, you know, jump in front of a bus later. I'm saying if I lived healthily to my sort of 10, I think that's it's sufficiently inaccessible to current technology. I don't think it's going to get anywhere soon. But I mean, as I say to students in my GR course, if you do manage to get that, don't bother doing the assignments. Just put my name on the paper and stick it on the archive. That's fine. Why do we have 3 generations of matter? Right? I mean, we don't actually. I don't know. Do we need them? Right? It's not. Why? What? Yeah, there could be 5. Or there could be 1, or there could be 3. You know, it doesn't make sense. There was an intriguing paper from MIT, which I talked about yesterday, which is not very convincing, but it was the first paper that showed that you might get the structure of the CKM and PMNS matrices from quantum information principles. There are lots of cases where quantum information extremization gives you something interesting. So in ADS CFT theories, entanglement in a conformal field theory on the boundary of a spacetime gives you the geometry of the spacetime and so on. And when you apply these ideas to particle scattering, you seem to get hints that the relationship between Standard Model parameters might come from something to do with the structure of quantum correlations in nature, but it's highly speculative, and it's something we're exploring a lot at the moment, and it's not yet thoroughly convincing. It might just be that you're seeing a bunch of numerical coincidences. Why are there 3 or 4 forces? Why not 1 force? You know, I mean, Lego uses 1 force. I can make anything out of Lego, right? Or at least my kids can. It can't explain dark matter. I think that is something that we're going to get something on in the next 10 to 15 years, right? From everything that we have. And that's partly a statement about the technology that we have to really exclude the obvious options and push beyond them in the next 15 years. And that includes, you know, I spend a lot of time now at high-end astrophysics conferences that you know, it's a massively, hugely, rapidly evolving field. You've got CTA coming online already, being built to capacity over the next few years. You've got the PV regime being probed. You've got neutrino astronomy opening as a field. You've got gravitational wave astronomy maturing to the point where you can actually study phase transitions in the early universe that are producing gravitational waves in non-standard ways. So if we can't get something out of that, you know, not enough people are going into the office, I think. We can't explain neutrino masses. You know, I don't know. I'll be interested in my colleagues' view on this. I've never been that concerned about this. It is absolutely important to study neutrinos as a sector, but I've always thought that the Standard Model should have right-handed sterile neutrinos. I think it's ugly if it doesn't, and there's a very natural explanation for the mass in that case. I think the biggest issue with the Standard Model is that it needs a ridiculous fine-tuning to get a Higgs mass of 125 GeV, right? So I talked earlier about these loop diagrams, and if I have a Higgs merrily rolling along, I get this kind of loop diagram where it, you know, can make fermions and sort of go back again. And I can calculate the effect of that diagram, which is to shift the mass of the Higgs. And if I assume that the Standard Model is some theory valid up to some energy scale lambda, the shift in the Higgs mass, do I mean lambda? I probably mean, is that a lambda or a gamma? I'm rubbish on Greek letters. That's a gamma, isn't it? No, it is a lambda. I was right first time. Right. Okay. You know, I went to a sort of British school for plebs where we didn't do these letters. We had to learn them later. Okay. it goes as the square of that cutoff scale. So now it could be that the standard model is correct right up to the point where quantum gravity enters, which is somewhere near the Planck scale. And then the Higgs mass is sensitive to the Planck scale squared. And the only way to get around that in the standard model is absolutely absurd fine-tuning of the parameters to make sure that doesn't happen, to cancel off these corrections. So that's not a good thing for, every time we encounter that kind of thing, the theory's wrong and there's some other explanation, right, which might come later. So most of the attempts to think about BSM physics without data to guide them, right, have involved trying to solve this theoretical conundrum in the standard model, right? Okay, so I think the big unknown is not, are there new particles beyond those of the standard model? Yes, I mean, there are. To me, there very obviously are. I mean, yeah, we've never actually explored a range of energy scales without discovering something new. We're in something of an anomaly, actually, in our discovery sort of trickling out now once every 50 years. I think there's good reason to believe there's something before about 100 TeV. You can ask me at the end if you're interested. But it's that problem. It's not, are there new particles? It's what is the mass scale of the new particles? What's the experiment or the astrophysics observation or the collider or anything that I have to build to see evidence of those things? And that's not obvious. Now, pre-LHC, you had to see something at the LHC that was either the Higgs mechanism or something else, because the standard model broke if you didn't see that. It had something called unitarity violation, right? So you had to see something. You absolutely did. That's not necessarily true where we are now. It's an opportunity. It's scary for some people. I think it's an opportunity to look at all ways that we might be able to access mass scales of interest for new physics. So the Higgs fine-tuning problem does actually pick out the TeV scale as something interesting because it's close to this electroweak scale of the W and Z and the Higgs masses. It's also, there are good reasons to believe that dark matter, if it is actually particles, is around this scale. And that's to do with the equations of how you get the relic abundance that you see in the CMB correct. Right? So the search is on for what we all call BSM physics, beyond standard model physics. So I'm going to go through the various options that people have played with in a kind of very high level way. One of the earliest ideas was grand unified theory. So when you see sort of pop science articles on the theory of everything, it's connected to this stuff. Now, I told you that the forces arise from symmetries in the standard model. You can write down, just crudely speaking, I'm not going to put the various indices on because there's sort of fine details to this, but broadly speaking, you have a symmetry group for the standard model, which is like an SU3 cross an SU2 cross a U1. And if you know your theories of Lie algebra and so on, you can understand what these things mean. But I should be writing indices here because I have an L here or whatever, I have electroweak symmetry breaking and it mixes things up. But that's broadly speaking the group. And there's another idea, which is that the strength of forces that I see changes with the momentum exchange in the experiment. Is that a familiar idea to you? It's actually a physical idea. It's a mathematical idea, but it's a physical idea as well. I mean, if there's an electron in Adelaide and I view it from here, it looks very much like a point particle. Right? If I zoom into very close distance scales, I start to resolve a cloud of virtual particles around the electron, which quantum mechanics is allowing to happen because of fluctuations in the field, and it starts to screen the force. Right? So distance scales, of course, in the uncertainty principle are like momentum scales. If I do an experiment with a higher momentum scale, it's like I'm probing smaller distances and the strength of the force changes, right? So the forces run, we have these things called renormalization group equations, which even tell us how the strengths change. And you can see that they almost unify at high energies, but not quite. So the idea is, can I embed that symmetry group in some kind of larger symmetry group where I'd actually unify the forces, and the universe was born with a single force, and it's only as it expanded and cooled and underwent phase transitions that I start to get these separate effects. And that's a familiar idea for anyone who does material science, right? It's the universe as a material. The problem is that the simplest ideas are just incompatible with experiment. I mean, if I take SU5, which is a simple way that includes that group, the proton decays really quickly, right? And you're probably sat here thinking, I wish my protons had decayed quicker. But it's wrong, right? It's wrong. And so people still play with this idea, but it starts to go beyond the point where it was an elegant answer. Do you see what I mean? I mean, if you take something and you start adding the epicycles, you get somewhere else. But it's still a very powerful idea, and you can look at supersymmetric guts, and you can do all sorts of things to it. But nature hates our guts so far. Okay. You can look at composite Higgs theories. Actually, that equation I saw that was sensitive to lambda squared for the Higgs bosons corrections comes about because it's the only fundamental scalar. So in fact, there's nothing special about it in that regard. Any fundamental scalar would have similar issues. So maybe the Higgs isn't a fundamental scalar. There's an idea that the Higgs boson might have some substructure, and you can do this by having new quark-like constituents and some new heavy version of QCD with fundamental degrees of freedom that you haven't accessed yet. So I did some work on this with James Barnard here in Melbourne a few years ago before he became a ludicrously highly paid data scientist. And my student Daniel Murnane, and it's a credible idea. It actually looks a lot like the theory of chiral symmetry breaking in QCD and the relationship with the pions, for those who know that bit of physics. But you can construct the theory. You can even have sort of mixtures of elementary and composite objects, and you end up with partially composite things. So the top quark could be a partially composite object. And we were able to show things like the regime where you minimize the fine-tuning of that theory also gives you interesting results for dark matter and things like this. So it's an interesting scenario. It's quite complicated. But at the LHC, you could discover the new meson-like resonances that you get from these new QCD-like degrees of freedom. So you can actually test this quite well at the LHC. And indeed, it's been tested and has failed the tests so far. But of course, it could just be a higher mass scale. All right, supersymmetry is famous. Of course, it's a hypothesized symmetry that connects fermions and bosons. There's something called the Poincare group, and that's a mathematical group that includes Lorentz transformations, for example, translations, rotations, boosts. And you can add, supersymmetry sits in that group, and it's the last symmetry in that group we've never observed directly. And it's literally a symmetry that sort of, you have a symmetry operator that can turn fermions into bosons and vice versa. If you go to Paris, I was in Paris recently on sabbatical, there's a cemetery where you can go and visit Poincare's grave. And in the same cemetery, there's the French pop star Serge Gainsbourg. Fantastic figure. So everyone is queuing for Serge's grave and no one's bothering about Poincare, obviously. Yeah, exactly. I think Samuel Beckett is in the same. So, and just all these ludicrously famous people. So someone one day has to write a play about it's Halloween and they all come back as ghosts and what the hell they talk about. Anyway, the Poincare group is important. Yeah, that to me is quite a natural motivation for something like SUSY. It naturally cancels off the corrections to the Higgs mass, so it solves the hierarchy problem. It unifies the forces, and it provides a dark matter candidate. So, there are many, many reasons to like this theory. What it does is it literally introduces a slew of particles to hunt for at the Hadron Collider and well beyond the Hadron Collider. It's something that CTA will be looking for. So if I have an up quark, I literally then have scalar partners. So, this is now a boson partner to the fermion. I get up squarks. Because of the number of degrees of freedom in a spinner, which describes a spin half object, I actually get two of these things. So then I get two up squarks, two charm squarks, two top squarks, etc. The force particles also get partners. The Higgs. There are more Higgs bosons in SUSY because I have to have at least two doublets of Higgs fields to make the theory work. So I can look for the extra Higgs bosons. And these things sort of mix because of quantum mechanics and whatever, and you get a dark matter candidate, which is the best one's probably that. There are others, but when people talk about supersymmetric dark matter, they're usually talking about that. So then the mission is, you have this collider, go and find them, right? And people have looked for SUSY now for 15 years, and I think I will give you later my view on what that's actually told us, because I maintain it's very early days, but we'll come back to that. Somewhat ontologically wackier thing is extra dimensions, right? You can write theories with extra spatial dimensions, and there are good reasons to do this. Yeah, even if you're sober, there are theories that really work better in this kind of thing, and it's not obvious how they solve the hierarchy problem, but they do. So the idea here is that you have some 4D Minkowski spacetime embedded in some bulk spacetime, which could be 5D or it could have extra dimensions in it. Gravity sees all the dimensions, and that's why gravity is a lot weaker than the other forces, because gravity is, if you like, sort of diluted in this bulk space, and we see some remnant effect of the gravity on our 4D world, but we're not sensitive to the full 5D behavior, right? So this is where things like black hole production at the LHC comes from. When I was doing my PhD in Cambridge, that stuff was being worked out for the first time, how you would produce them, how they would decay. And what would happen at the LHC if you could make a microscopic black hole, which immediately Hawking evaporates. And you can then actually, they were showing, this is another student, Matt Palmer, I think it was, Andy Parker and Brian Weber. And you actually see a Planck black body spectrum in the sort of full momentum of the decay products. You get this imprint of the Planck black body nature of Hawking radiation on the fundamental particles that are produced, because it's just Hawking radiation. And you can also, it's also flavor blind, right? Because it's Hawking radiation. So there are very, very clear signatures of black hole production for the LHC. One of my favorite signatures is just that you produce an enormous density of particles when a black hole evaporates, and it would have broken the tracking software because it couldn't cope with that number of tracks. So had the tracking software gone down, I'd have said, no, you should be delighted. We've made a black hole. Yeah, you can also look at other signatures. You get these kind of Kaluza-Klein resonance signatures where you're seeing, one way to think of this is you're seeing kind of reflections in the extra dimensions of your existing particles, and you get evenly spaced resonances that tell you something about the geometry of the extra dimension. So I have a PhD student at the moment looking at warped Randall-Sunder models and this kind of thing, but he's actually looking at cosmological implications rather than LHC. Okay, what's happened over 10 years of not seeing striking evidence for any of these things at the LHC is sociology kicks in, right? And people sort of lose faith. If they have something called faith in these models, I think most of us are agnostic. We just take what's a mature testable theory and we go and test it, right? So one other thing you can do is you can say, okay, look, what is the standard model? It's at least the low energy version of something that's a high energy theory that might one day include gravity. So it's what's called an effective field theory. And there's a whole landscape of tools for constructing effective field theories, because basically we know that you can separate short and long distance effects in physics theory. So I can write extra terms and add them to the standard model following the rules that a gauge field theory textbook tells me I have to follow. Right, the mass dimension of every term should be 4. It should have its Lorentz indices contracted. It should be gauge invariant and so on, right? And so I can just add terms to the theory and then test them. And that's like an agnostic way of testing new physics, right? You're just adding the interactions that are allowed and trying to see if there's any hints of anything new. And then later you might hope to discover what that thing is. You're probably familiar with the fact that at low energies, the weak force, was first described by Fermi's theory, which just had a contact interaction, right, between particles. And as you get up in energy, you realize there's actually a massive particle mediating the interaction. But you have to get up to energies of the scale of the mass of that before you start resolving this, right? So similar idea, you can add contact interactions to the standard model. For dark matter affected field theories, you can add explicit mediators between dark matter and the standard model, following the rules, and it's all fine. So this is a hugely popular way to sort of model any kind of BSM physics. There are dark matter effective field theories. People have worked out the general terms you can add as you go higher in mass dimension for the standard model. For if you look at presentation of results in flavor physics, standard way to do that is with an effective field theory. And what LHCb is telling you at the moment is that actually you do have very, very strong evidence that you're not seeing the standard model when you do that, right? Very strong evidence, I think. We had a Gambit paper that Csaba reminded me, we rejected the standard model at 6 sigma or something. And the results have only got stronger since then. So there's something going on, I think. It's a difficult calculation to get the standard model prediction right. That's why it's not cut and dried. I don't know, you probably have a similar thing. You can see where the field is going from the archive, but you really see where it's going when you hire postdocs. You get a grant and you hire a postdoc every 1 or 2 years, and most postdocs, when we hired in the last round, were working on EFT topics, because that's really where the field's going, this general way of testing new physics, and it's a good idea. Yeah, and it works at any energy scale. I can do this for low energy experiments, and I can compare that to LHC results, and it's a nice way of doing it. Okay, so how do you then discover physics at the LHC, there's two ways to do it. One is to try and directly produce new particles and measure them. And if they decay visibly, we've already seen how you do it. You just take the invariant mass of decay products and you look for bumps, right? If they decay semi-invisibly, if I make a particle which is producing dark matter and something visible, I have to do something else. So we can measure in Atlas and CMS what's called the missing energy. We have particles coming in like this. So the full momentum in the transverse plane beforehand must be 0. So it must also balance afterwards. And we can actually look in the detector and see if there's any full momentum missing, if you like. And you can make neutrinos in the standard model. So there's some expectation that you get missing energy just in the standard model. But SUSY would produce way more on average, right? So if I look at this distribution, it's never quite this simple. But if I look at this and I start seeing loads of events piling up over here, I'm clearly inconsistent with the standard model. And it doesn't tell me what I've produced, but the work we do in Gambit and other things is very sophisticated in being able to unwrap the physics that's doing that from a very few distributions, right? Typically, you have to go well beyond this. You have to construct very fiendishly clever functions of 4 vectors that isolate the BSM physics from the standard model physics to get a better signal to background. The other thing is that when they turned the Tevatron on, they saw that. They didn't see that. And it's because their missing energy calibration was woeful, and which they knew it would be at turn on. And so it was only after a few months that you actually got this distribution. So the problem with this is it's really sensitive to everything you're getting wrong somewhere in your detector. So it's a very difficult thing to think about and get right. But it's, you know, that the groups that do that at the LHC are now doing it exceptionally well. The other thing we saw is that I get these loop effects, right? So if I had new particles running in loops, if I measure things very precisely, production rates, branching fractions, the basic bread and butter quantities of particle scattering, I will get sensitivity to new particles that can run in those loops. And what's exciting about that is I'm probing nominally somewhat higher energy scales in that kind of process than I am there. So if I have particles I couldn't produce directly because their production rate's too small, I might still see evidence for them here, right? So this is why it's important. And as I keep saying, LHCb is seeing stuff that's just not consistent with what we expect. And if the standard model calculation is correct, we've already seen new physics in those systems. So that, you know, the onus is on the first bit there, and that's difficult QCD problems. Okay, so the open questions for Higgs physics are these in the next, just keeping on the clock. Yeah, this is really the next 15 years and the next collider. So this is the end of the LHC and the next collider. Is the Higgs boson really the standard model Higgs boson? The particle we're seeing absolutely does look like it's a standard model like Higgs boson. I think that's fairly well settled, but there's still extra things we can measure. This definitely isn't settled. Is the Higgs field really the standard model Higgs field? And what I mean by that is the potential that I have to add to the standard model equation has a very specific form. Is that the potential that we've seen at the Large Hadron Collider? And the answer is we don't know because we can't measure it. You have to be able to measure the self-coupling of the Higgs to extract the parameters of that potential. So by the very, very end of the LHC's run, it's possible we might be able to say something with a large error bar about that. I think that's still the status. I think Matt Dolan just, you know, across the city in Melbourne Uni was thinking about this a few years ago. That's really the job of a future lepton precision collider that can do that, right? So that would give us the Higgs potential. It would also give us the precision to really test this idea to destruction and see if there's anything new. And I actually think it will find something new. I think there's something fishy about the situation at the moment. Are there extra Higgs bosons? We've already seen in SUSY, I need 5 Higgs bosons to get the theory to work. What we showed in a paper recently, and another paper showed, is that there's a quantum information principle that if it was correct, it naturally explains why 2 Higgs doublets would make 1 Higgs boson look like the standard model Higgs boson, and all the others would be somewhat decoupled. You could still find them at the LHC, but they wouldn't disturb the branching fractions of the standard Higgs boson. That's due to something called the alignment limit, and it emerges from either minimizing entanglement or conserving something called non-stabilizerness. So again, you can ask me about that. So this idea that the structure of the theories that we observe in the universe might be connected to the patterns of quantum correlations that the universe is able to produce has had some interesting things to say. We just don't know if these principles are true yet. We're just trying to spot interesting examples. The other thing is the Higgs boson could actually be our first portal into dark matter. There are theories where the Higgs boson is the only particle that dark matter interacts with in the Standard Model. So the Higgs interacts with Standard Model fields, it interacts with the dark matter. You can make the dark matter in the early universe. It can be a thermal dark matter candidate because it thermalizes, because it can interact through the Higgs and so on. And that's a very testable idea. So this is the LHC schedule out to 2035. We are approaching the next long shutdown period. So it's done 3 runs so far. This purple line is in, as usual, you spend a lot of money in a degree to learn fancy words for simple concepts. This is the total amount of data we've collected at the LHC, right? That's how you think about this thing in purple. That's the instantaneous rate of data collection, right? Which is not the same thing. Yeah, that's how bright is your collider, if you like. What's the luminosity, right? But look, we come up to here, we have this long shutdown period, and then suddenly we start collecting data at a vastly higher rate because it's being upgraded to the high luminosity LHC. And to all intents and purposes, that's like having a new collider, right? You're collecting data at a much faster rate. All of the things I've talked about in terms of BSM physics are rare processes. So you can make rarer things happen more often by going to higher energy, or you can go to much higher luminosity. And the high luminosity thing is the game here. And your rate of data collection shoots up, and there's another break, and then you sort of go up again, and it goes out to 2040, right? So the LHC has taken 15% of its total expected data set, right? For things like testing dark matter at the LHC, which we know has to be weakly interacting, obviously it's not dark, that's an exceptionally rare thing to do at the LHC, and it's very, very early days. It's weird when you've been running something for 15 years, and if you integrated the number of person hours that's gone into hunting for things at the LHC, it's a very, very high number. But it's an extremely early point in the history of the collider and what it can do in future, right? So if there's one message you take away, it's that this really is a flagship, energy frontier program for the next 15 years. I mean, this will see me comfortably up to sort of semi-vague retirement of usefulness, certainly, right? And of course, the one thing I can't touch on today because I'm not too heavily involved, but I know Ulrich and Peter certainly probably have more local expertise, is the current European strategy and the future direction and how they're deciding between the different options for the next colliders, right? And those are precision machines rather than the LHC, which is a kind of scan all energies at once discovery machine, right? I think I have 2 or 3 minutes to just give you a couple of examples of how we actually take this information and learn about fundamental physics. So there's one thing missing from this slide, but the entire future of collider physics is somewhere in this. We might discover a new particle decaying purely visibly. My guess is that has something to do with electroweak symmetry breaking, which is the expensive word for the Higgs mechanism, okay? We might discover something decaying semi-invisibly. If it's semi-invisible, I bet that thing's a dark matter particle. That would be my first thought, right? The extra one missing here is we might discover something in loop corrections and we definitively pin it down and it's definitely new physics and we have to work out what that thing is, right? Or we might discover nothing, right? And that's somewhere the future history is there. What can we do with that information? Well, we can combine all of the data that we have from all sorts of experiments and test theories of physics. So even if the LHC announces a discovery tomorrow, and I'm not aware of one, I'm just saying this hypothetically, right? If it announced something tomorrow, any theory that explains that has to also explain why we haven't seen it for the last 15 years, why LEP didn't see it, why the tevatron didn't see it, why there's been no astrophysical signatures, why there's been no cosmological signatures in a theory that would have had things to say at the time of recombination or something, why I haven't seen it in high energy cosmic rays, why I haven't seen it in the neutrino or flavor sector, right? So we have this idea that we're in the era of having to put vast amounts of data together. And in 2012, I mean, Csaba was at ICHEP, I was at ICHEP. Peter, were you at ICHEP in 2012? No, you weren't. You were at CERN, but you were there, of course, yeah, because the Higgs discovery was announced at CERN to Australia because we had the conference here, right? And we basically got together on the South Bank and over beers, thought, how would you design a system that can generally take all data and gets the right theory of physics from all the experiments that we have. And 13 years later, we're now, this is already out of date. We have more than 80 people on loads of different experiments, loads of different theorists, and we've made a very general global fit framework where you can stick in lots of data and easily extend it to other things and learn about theories of physics. So if I stick in the dark matter effective field theory, this is the mass of the dark matter candidate, this is its relic abundance, you find that you can't have a WIMP that saturates the observed relic density if its mass is below about 100 GeV, and that's because of, astrophysical experiments. The LHC sort of ruled out this region, but there's lots of viable space left, and CTA will start honing into this chunk within a couple of years, or so. But, WIMP theories are very much alive. My favorite example is actually this, and this is probably the last 60 seconds. The question I get asked by astronomers more than any other, probably, well, the first one is, can you go away, please? The second one is, you haven't seen Susie for 15 years, so you must have been able to say something about the mass of the neutralino, which is your dark matter candidate, right? And so this is the data up to 2017, and I have to say to my LHC colleagues, we're updating these results now and they will change. But at least after the first sort of run and a half of the LHC, this is the mass of one of the SUSY particles, this is the mass of the dark matter. All of this plot would be yellow if there was no exclusion, and it's nearly all yellow. There's some weak disfavoring over here, but it's fine within 1 sigma. So what we found is that, and this was 10 years, I think, of searches at this time, or nearly 10 years, there was no constraint at all on the mass of the supersymmetric dark matter candidate. And I'll come back to this thing again. It's early days. It's a weak production mechanism. To pull a signal out, which is 1 billion times smaller than the background, you have to optimize very, very, very heavily on a particular guess of what the properties are. So all the searchers had used this particular guess. And of course, you've missed this bulk of options over here. And even if you go after that one, you're going to miss this one and so on. So I've spent a lot of time thinking about how you would do this in a more general way. And you're in the phase where lots of things partially work. Unsupervised machine learning works, but it works not that great because it will never outperform a supervised technique, etc. Right? What was even more intriguing is you could run this analysis and say, is there evidence for a signal? And there was evidence for a signal in the data. And I'm not claiming a discovery of anything. We didn't trust this signal. It's probably statistical fluctuations. Indeed, they've gone away in the new analysis. But the key point is, what sort of signal would have been missed by the searches people had done? And the signal that was picked out had all of the electroweak enos light. So all of these super partners of the force particles in the standard model were all fairly light. And people had assumed that they weren't. People had assumed that most of them were heavy and you were only searching for a few of them. So they missed that option. But the option where you have lots of particles light and within range of the LHC is the joint Christmas and birthday scenario for searching for Susie. So we've been obviously working closely with experimentalists to close these gaps. And my message is that I can give you common garden, very good theories of BSM physics that people are saying are dead and are absolutely viable, and we should search for them in the right way. Right? That's the message at the LHC. And we've only taken 15% of the data, and there's a vast landscape of potential discoveries that could come. And whether you think they're going to come is just purely up to your prior. Right? Or if you're a frequentist, learn to be a Bayesian and then attach a prior. Right? Okay. I'm not going to summarize because I've told you everything, but that's it. Yeah.
Very entertaining talk. Are there questions, please?
Really great talk for me. I'm an astrophysicist, so I learned a lot
excellent.
from that. And I was pleased to hear you say regarding dark matter, if indeed it is particles.
Yeah.
So are you open to it not being particles?
Yeah, I'm completely agnostic. I can tell you some of the other work I've done that's non-particle-like. We looked at primordial black holes, for example, and you know that they're pretty heavily constrained over lots of the mass range. But what we found is that some of those constraints were wrong. So we went back to, we were interested in constraints on Hawking radiation at the time of recombination. And we looked at those results. And if you varied the lambda CDM parameters at the same time as you were, looking at this behavior, you found you could weaken the limits by an order of magnitude. And you could still have viable primordial black hole dark matter with viable lambda CDM parameters. Right? primordial black holes still require new physics because you have to make them, but that's very speculative, high quantum gravity type physics. It's not WIMPs that are accessible at the TV scale.
Okay,
right?
what about general relativity itself?
So that's also an excellent question. So there's modified gravity I don't like, and there's modified gravity I like. So to me now, and I work with cosmologists in Gambit quite heavily, and they've informed this view. So I'm really parroting an opinion. But the fundamental test of a gravitational theory now is, can you get the matter power spectrum correct from some pattern of perturbations in the CMB? It's so things that just say I can shift Newton's law with a term and I get this behavior in galaxy rotation. That stuff I don't like. But what's interesting about GR, I'm lecturing it again at the moment. There are two assumptions baked in, just put into GR, right? One is I have zero torsion, and the other is I have a metric compatible connection, right? And both of those are assumptions I can do. But you can also get rid of both of those assumptions. And there's a whole hierarchy of gravity theories that result from either adding torsion explicitly, and including the effects of a torsion tensor, or adding non-metricity of the metric tensor. And one of those ideas was what Einstein was doing for much of the rest of his life. It gives you something called teleparallel gravity. And there was great excitement back in the day because you get 6 extra degrees of freedom. And he was trying to put electromagnetism in because that's the number of degrees of freedom you need. And then, of course, some clever bastard comes along and says, no, they're redundant. You can transform them away. But people, Will Handley was telling me this, people are still very much studying these theories and they have things to say about dark energy. They might, they would, of course, modify the FRW metric from the classical gravity piece, right? So I think, and he had a postdoc that was doing something called Poincare gauge theory, where you gauge the Poincare group, but the calculations are so hard, he says it took about 3 months to work out if you get a star, right? But no, there really is. There's this whole area of sort of non-standard gravitational theories, which is really quite viable. And there's also something else about, GR is written in differential geometry, but some of these theories just look like flat space-time and are mathematically equivalent. So if Feynman's generation had done gravity, because Einstein didn't get there, they would have actually just looked like some kind of classical gauge theory, right? So there's a lot to think about there. I think that my hunch is they're more relevant for dark energy than they are for dark matter, but who knows? Right?
Let's talk over coffee, huh?
Yeah, all right. Oh, yeah, sure.
Thanks.
Are there any theory? I'll read it out for those in the room then. Are any theories trying to resolve open questions can be simulated, modeled in condensed matter or ultra cold atomic gases? If yes. Right. So I can only answer this because I saw a talk when I was still in Cambridge a few years ago where they were simulating things in condensed matter systems, excitations or resonances, so on, that basically resembled the mathematical structures you get in 5D theories. And they were able to show that our field theory understanding of how those systems work is actually how it works when you do this in some kind of simulator system. This is something I'm actually really interested in knowing more about from the quantum information perspective and so on. So if you've got anything that you want to email me about, do it, please. Yeah, that'd be good.
Other questions in the room?
I just thank you for the nice talk. I just wanted to pick up on something you said earlier, which was about there being something, you being pretty confident that there's something in the TeV range. Could you expand upon this?
Yes. So beyond the usual arguments, hierarchy problem and so on, this is really connected in my mind with supersymmetry and its viability. So what's the easiest way into this? So the mass of the Higgs of 125 GeV is a data point for something, right? Now, if that mass had been 135 GeV, the simplest SUSY theory was dead. Because the argument that we're given that you have these radiative corrections which shifts the mass of the Higgs and they're cancelled off by supersymmetry, that cancellation is actually really good. And it cancels them off rather too efficiently. And the Higgs mass should be something like 80 or 90 GeV, which is where the W and Z masses are in canonical SUSY. So then I have to basically raise the mass of the top squark is the dominant effect on this. I have to raise that mass to get up to 125 GeV because I'm reintroducing some level of these corrections, right? So actually, the easiest way to explain the Higgs mass in the simplest SUSY theory is to have the coloured squark masses up at about 10 TeV instead of 1 TeV, and that difference is crucial because 10 TeV is kind of outside of LHC range, but it would be got by a 100 TeV collider, right? So to me, 100 TeV, 2 orders of magnitude above, sort of where you've got well, the difference between 80 GeV and 100 TeV is much bigger. I think that's what you'd really want to explore this landscape and rule it out. And I'm very, very confident there's something in there. Actually, it's a hunch, but because of this Higgs mass argument, it's an intriguing thing, right? For those who are interested, I mean, this is a quite random tangent, but you might be aware that you can look at the vacuum stability of the universe, and this is something that Csaba spends a lot of time thinking about. And since we've measured the top mass and the Higgs mass, we know that we're at a very, very precise point in the phase diagram where we're just at the precise point that would give a stable vacuum. And that's a very, very profound thing that does not happen by accident. And I suspect it will be obvious when we have the next theory of physics. I haven't yet related that to a mass scale of something that we'd have to see that explains that, but other people have thought about it, I think.